and welcome to Make Learn 360. Please, if you have joined, we are going to start soon. You can leave me a message, hello, so that I will know that you are connected. Thank you. All right. So in today's tutorial, we are going to look at algebra, okay, basic engineering mathematics. So there are several steps, but for the purpose of the tutorial, I'm going to select, some key areas which can help you prepare for your exams. All right. So now we want to start with okay. So I think it's good to start with the complex numbers because at the end of the day, that is the most important thing to start with. We could look at the principle of mathematical induction. Okay, but please let's look at complex numbers. All right, so we want to start with complex numbers. All right, so I'll be starting in 5 minutes time. Thank you. All right, So we are about to start. All right. Okay. So to begin with, we want to look at the complex numbers. So I want to give you some key, some key things you must know to be able to solve questions about complex numbers. At least we would start with the basics. So this is just a review. We are not going to cover everything. So first of all, what do we know about complex numbers? All right, so we are just starting with complex numbers. All right, now we know that for a complex number, it has got two components, which is the real part plus the imaginary part. So let's say x plus y I. All right, so the real part is the x, and then the imaginary part is the y. So imaginary. So basically that is it. And then we know that the I is actually the square root of -1. So this is where the whole complex number started, right? Okay, so then let's go back and then okay. All right, so okay, so let's start with some basic complex numbers. So first of all, all right, so we want to look at the basic addition and then the basic subtraction, and then we will look at what we call the modulus and then the argument. All right. So then let's start. So let's say I have a complex number z1, and then I have z2, and then I have z3. So let's try to play around this. Okay, let's just try to play around it. All right, so given z1 and then z2, so I can basically say that z1 plus z2, let's do that. So z1 plus z2 will be what? Okay, so now to do the first part, what you are going to do is that you will just add the real part to the real part, and then the imaginary part to the imaginary part. So adding the real part to the real part, we are going to get 2 plus all right, let me just write it together. So 2 plus 4i, that is z1, plus z2, which is 3 minus I. Alright. So how can I add the two together? So then it's going to be adding the real part, which is 2 plus 3, and then adding the imaginary part, which is 4 minus 1. Then you bring the I. So at the end of the day, it's going to be what? So if you do this, you are going to get 5 plus 3i. Okay, so that is basically z1 plus z2. So in other words, whenever you have a complex number, you just add. Whenever you are adding two complex numbers, first of all, you are going to add the real part to the real part, and then the imaginary part to the imaginary part. All right. Okay, so then let's move to the second one. So we are going to do the same thing. So z1 is 2 plus 4i minus z2, and then z2 is what? Z2 is 3 minus I. Alright. So again, we are going to separate the real part, which is what? 2 minus 3. And then you move to the imaginary part, which is what? So plus 4. Oh, sorry, it's minus. So minus 4 okay, let me do it this way. So the real part is going to be 2 minus 3. That is the real part. And then the so plus 4, I mean the imaginary part. So plus 4 minus 1i. Alright. Okay. So basically that is the complex part. So in other words, it's going to be 1 plus, so it's going to be 1 plus 3i. Alright. So 1 plus 3i. Okay. Z2 plus Z3. So Z2 plus Z3 is going to be what? 3 minus I plus. So we have Z3 as what? Minus 3i, right? But we can actually write minus 3i as 0 minus 3i. So that we will say that for the 3i, the real part is 0. Okay. Now we are adding these two. So you have to add the real term first. And then you are going to add the imaginary terms. Alright. So then this is what you are going to do. 3 plus 0. That is for the real part. Now when you come to the imaginary part, it's going to be plus so it's going to be minus I plus minus 3I. Yeah. Okay. Okay, I think there was a mistake with the second one because we were asked to subtract. So it was supposed to be 2 minus 3, all right? And then plus, so the imaginary part was supposed to be 4 minus I, which would have made it minus 1I. Let me put it that way. So in fact, this one was supposed to be 5. So it was supposed to be 1 plus 5I. So this is the correct answer, please. All right. Okay, so that is it. In other words, we are going to get so 3 minus 4I. All right. So that is it. So on and on and on and on. Okay, let me just do 2 minus 3, which is 3 minus I minus 0 minus 3I. So if you want to do this, it's going to be 3 minus 0, and then, you know, this one is minus I, but this one will be minus 3I. So it means that it's going to be, so plus minus 1 minus 3I. So it's going to be plus. In other words, it's going to be 3 plus what? 2I. Because minus 1 minus 3 is actually 2. Okay. So I hope you can do the rest here. So the idea is to review addition and subtraction of complex numbers with you. All right. Okay, so now let's look at the modulus and then the argument of a complex number. Okay, so whenever I have a complex number, I can write the complex number z as a real part and then what? An imaginary part, right? Okay. So then we want to look at the argument. All right, so please, when we say the argument is not a fight, some people think that argument is like when you have a fight with someone. No, this is complex algebra. All right. So let's say we have a graph. And then I have y, and then I have x. Then I decide that I want the real part to be here, and then the imaginary part to be on the y-axis. So in other words, this is like saying that you have got a component. Oh, sorry. So you have got a component along the x you have got a component along the x, and then you have got a component in the y direction. Okay, so then this now becomes, so it's like saying that I have x, I have, okay, let me say a and b. So let's say that I have a, I have b. Now let's call the magnitude r. Okay, so from Pythagoras theorem we can say that r squared is equal to a squared plus b squared. Okay, and then if there is an angle here, let's say theta, we can say that theta is going to what? The tan inverse of what? B divided by A. Okay, so now this is basically what we are saying. We can say that whenever we have a complex number, this complex number r will have a cosine theta along the x plus b sine theta along the y, but we are calling the y as what? The imaginary axis. Is that right? So basically the y is our imaginary axis. Okay, now so the argument, which is r, will be the square root of a squared plus b squared, and this r is what we are calling the modulus. All right, so this is what we call the modulus, and then theta is equal to the argument. All right, so then we have got our modulus and then we have got our argument. All right, so now let's continue. So now it's very important to know that whenever you have a complex number, then in basic terms, so in basic terms, to find the argument, you just need to take you just need to take the square root. Okay, you just need to take the square root of x squared and y squared. All right. Okay, so let's say that you have been given a complex number and then z equals what? So let's look at this question. Z equals 2 minus 3i. Oh, sorry. So z equals 2 minus 3i. So if I have z equals 2 minus 3i, then what is the argument? Or in other words, what is the modulus and the argument? So the modulus or the magnitude is given by what? the square root of 2 squared plus minus 3 squared, which is what? So I want you to pick your calculators, and then, so what will be the value of the square root of, so it's going to be 4 plus 9. So let's say the square root of 13. So that is the magnitude. All right. And then if you want the angle, it's going to be tan inverse of so the tan inverse of b over a. So the tan inverse of 3 over 2. And what is the tan inverse of 3 over 2, guys? What is the tan inverse of 3 over 2? All right. So I'm waiting for the answer. So if you do everything correct, the tan inverse of 3 over 2 is going to give you 56.3. But it's going to be negative because of the minus 3. So if you plot it, actually, if you plot this, so this is what you are going to get. So you are going to get here is the here is the real axis, which is 2, and then the imaginary axis is the y. So the negative will come here, which is what? Minus 3. So if you look at it carefully, you will see that the x component is here and the y component is here. So then our magnitude is somewhere here. And this is the reason why it is negative. All right. Okay. So now let's look at another question. All right. Okay, so all right. So let's look at the complex conjugate. But before we do that, let's look at what happens when you multiply a complex number by another complex number. So let's say that I have a complex number z1, which is a1 plus b1i, and then I have another complex number which is a2 plus what? b2i. Okay, so how can you multiply z1 and z2? So it's going to be z1 multiplied by z2, which is what? a1 plus b1i. Then you multiply it by a2 plus b2 so a2 plus b2i. Is that right? So to get this, you are going to do this. So you are going to distribute a1 to what? a2 plus b2i, and then b1i will multiply what? a2 plus b2i. All right. So from here, what do we see? So we see that if I multiply z1 by z2, I'll be able to get what? a1 a2 plus what? a1 b2i. Then I'll multiply a2 by b1i, but I'll get what? a2 b1 I squared. Now interestingly, if you multiply z1 by z2, we know that a1 plus a2, but what here? You realize that we have minus because I is square root of minus 1. This means that I squared will be minus 1. So that I have a2b1 plus a1 b2 plus a2 b1 I. So in other words, if you multiply two complex numbers, you end up with a complex number, and then what? So you get a real part and then an imaginary part. All right. So that is what happens when you actually multiply complex numbers. But before we proceed, let's look at something interesting here. There is something which we call the conjugate, right? The conjugate. So now, first of all, let's look at this together. All right, let's take an example. Let's say I have Z1. So Z1, they've done it already, but I want us to go through. So Z1, which is 3 plus 2i, and then Z2, which is, all right, so all right, so Z1 3 plus 2i, and then Z2 so Z2 is minus minus 1 minus 4i. Okay. So then it's going to be, if I multiply Z1 by Z2, I will get 3 plus 2i multiply minus 1 minus 4i. Now I will get, so 3 multiplied by minus 1 minus 4i plus 2i multiply minus 1 minus 4i. Okay. From here, I can say that Z1 multiplied by Z2 is minus 3 minus what? 12i. Because if you multiply 3 by minus 1 and then 3 by minus 4, and then so minus 2i minus what? So 2 times 4. Sorry. So it's going to be plus 2i okay, let me do it this way. 2i multiplying minus 4i. So it was supposed to be minus 8i squared. But what happens is that I squared is what? Minus 1. So then you end up getting plus. And then here becomes what? Positive. Sorry. So then finally you are going to get minus 3 plus 8 minus 12i minus 2i. And then okay, let me do it this way. So it's going to be minus 3 plus 8 plus minus 12 minus 2i. And then what is that? So minus 3 plus 8 is going to give us 5. Plus 12 minus 2 give us what? 10. Alright, so this is actually the basic multiplication here. Okay, so that is it. Oh, sorry for that. All right, so let's look at okay, there is another example here. Let's look at this last example. Okay, I think they have done it here. So let's go through. So 1 minus 5i multiplied by minus 9 plus 2i. So for this one, it's going to what? 1 multiplied by minus 9 plus 2i. So that I have what? Minus 5i multiplying what? Minus 9 plus 2i. So minus 9 plus 2i plus what? 5 9 45 I minus what? 5 to 10. So minus 10i, which is going to be what? Plus, because of the I squared. So finally we are going to get what? 1 plus 47i, which is the same thing as what is here. I hope the concept is clear. All right. So enough of this. Let's do the complex conjugate. All right. Okay, let's do the complex conjugate. So whenever we have a complex number and then we multiply it by its conjugate. By the way, what is the conjugate? So the conjugate of a complex number is actually the same as changing the sign. Okay. All right. Okay. So let's look at the conjugate. So the conjugate of a complex number is like the negative of the complex number. For instance, let's say that you have z equals x plus y I, or let's say you have z equals what? A plus bi. So the conjugate is going to be a minus bi. So simply put, the conjugate is nothing but just changing the sign. All right, that's all. Okay. All right. I want us to take some examples. First of all, let's multiply a complex number by its conjugate. So let's say I have a complex number a plus bi, and then I have a conjugate a minus bi. So I want to see what will happen if I multiply the complex number by the conjugate. Then it's going to be a plus bi multiplied by a minus bi. All right. So this is going to be So it's going to be a multiplied by a minus bi plus bi multiplied by a minus bi. All right. So now, if we multiply z by z bar, what do we get? So we are going to get a squared minus abi, and then this one also give us plus abi minus what? Bi squared. All right. So now from here we have a squared, so this will cancel this, and then minus bi squared, right? So the I squared is minus 1, so it's going to be minus minus, which will result in what? So plus what? B squared. This is very interesting to know that whenever you multiply a complex number by its conjugate, you get a squared plus b squared, which is actually the square of the magnitude or the modulus. So in simple terms, it looks like you are basically how do I put it? You have found the magnitude actually. So whenever you have the product of the conjugate and then the complex number itself, then you have got, you know, the magnitude actually. All right. Okay. So from here, let's try and take some examples. All right. So now let's come back to, so we are going to look at multiplication that is involving the complex conjugate, and then division. All right. So let's say you have been given something like this as a complex number. To actually simplify this, how do you do this? Okay, so it's going to be by the way, before you start solving this, the first thing to do is to apply what we call the conjugate. All right, so in other words, you will multiply the denominator by the conjugate. So let's do that. You are going to multiply, you multiply both the numerator and the denominator by the conjugate. So it's like -1 minus 4i divided by -1 minus 4i, right? So this is more or less like multiplying, yeah. So multiply the first two, multiply the numerators, sorry. And then don't forget that we just said that whenever you have a complex number multiplying its conjugate, then it is the same as what? The square of this plus the square of this. So even if we don't do the multiplication, we know that for the numerator part, for the denominator, it's going to be -1 squared plus what? 4 squared. All right. And then, so we will multiply 3 by -1, which is -3. So 3 by -1, and then 3 by 4, which gives us -12i. And then we will take 2 and then 1. So -2 multiplied by -1 is what? Plus 2i. And then -2i will go and multiply, -4, right? And that is what? 8i squared, which will be what? -8. All right. Why is it -8? Because if you multiply -2i by 4i, what happens is that you are going to get +8i squared. So because of the I squared, you are going to get minus. All right. So that is it for you. So it will be that is -3 minus 8 minus what? 10i divided by what? Minus I squared plus 4 squared what? 17, right? 4 squared is what? Oh, sorry. So it's going to be 1 plus 4 squared. And what is 4 squared? So that is 16. Yeah, so 17. One plus 16 giving us 17. All right. So our complex number now can be expressed as what? So minus 11 over 17 minus 10 over 17i. So why are we doing all this when the calculator can do this straightforward for you? Sometimes you may be given this in terms of variables. And so if you don't know how to do some of these things, you will not be able to actually solve it. All right. Okay. So then let's look at the polar representation of complex numbers, and then we will also look at how to add and then divide in the polar form. So Euler was able to show that whenever I have a complex number, okay, so whenever I have a complex number, let's say imaginary and then the real, then we can actually say that so let's say this is the real A and then there is imaginary B. So the magnitude is R, and let's say this is theta. So we can say that R is A cosine theta plus B sine theta I, because this part here is what? A cosine theta. Sorry, let's do it this way. So what we have here is actually R cos theta. Sorry. So in other words, A is equal to R cos theta, and then B is equal to R sine theta. So this can be rewritten as R equals R cos theta R cos theta plus R sine theta I. In other words, we can rewrite R as cos theta plus sine theta I. Okay, so this is actually the polar form. Whenever you have a complex number, you can represent it as r, which is the magnitude, multiplied by cosine of the argument plus the sine of the argument, and then you add the imaginary number, the I. Okay, now Euler is saying that e raised to the power I theta is actually cos theta plus I sine theta. So in other words, whenever you have a complex number, you can rewrite it as REI theta, which will be what? R cosine theta plus I sine theta. So in other words, this representation is coming from Euler, and then we call it the polar form. All right. So now I want us to do some basic I want us to look at some basic addition and multiplication in the polar form. All right. All right. But before we do that, let's look at how to multiply. Okay. So let's say I have R1, a complex number, which is, no, let me do it Z1, which is R1 into bracket cos theta 1 plus sine theta 1 I. And then also I have another complex number, which is R2 into bracket cos theta 2 plus sine theta 2 I. Then if I want to actually multiply Z1 by Z2, then what is going to happen? So now interestingly, Z1 multiplied by Z2 will give us R1 multiplied by R2, and then cosine of theta 1 plus theta 2. Okay, and then plus I sine theta 1 plus theta 2. In fact, this is very, very important, and then everybody must take notice of this. Whenever you are multiplying in the polar form, the product of the you first of all write the product of the magnitude. So the magnitude of the first complex number, the magnitude of the second complex number, you multiply, and then cosine of the angles. So you add the angles, and then plus I sine of, again you add the angles. Okay. And then if you want to divide, so for division you actually subtract. Okay, so this is how it's going to be. If you want to divide Z1 by Z2, it will be R1 cosine theta 1 plus I sine theta 1, all divided by R2 cosine theta 2 plus I sine theta 2. All right. So now from here, what can we say? It's going to be R1 divided by R2 cosine theta 1 minus theta 2 plus I sine theta 1 minus theta 2. Okay. So please let's take notice of these things. Again, Z1 is R1 E I theta 1. Let's say this is another complex number. And then I theta 2. So we are going to multiply in the polar form. So Z1 multiplied by Z2 will be R1 R2 EI theta 1 plus theta 2. And then if they divide for this one, it will be R1 EI theta 1 divided by R2 EI theta 2, which is what? R1 over R2 EI theta 1 minus theta 2. Okay. So in fact, the idea is that I have given you three forms of a complex number. You can represent a complex number in three forms. Number one, Z equals X plus I Y. This is the first one. You can also represent a complex number by R into what? Cos theta plus I sine theta. So this is also another form of representing a complex number. And then finally, you can represent a complex number using Euler's identity. So please, these are actually the same, but it depends on where you are actually dealing with. Okay. All right. So all these three are the same, but it depends on what you are doing. Okay. All right. So I think at this point we can take some questions. But before we do that, let's look at the Livestrem. And then I think we will end it on this chapter. So the Livestrem is actually saying that if you are given a complex number x plus I y raised to the power n, it will be difficult to do this. If you try to do it, it will be very difficult. Let's say you have been given z equals 1 plus I raised to the power 1000. How will you be able to do this when you want to do it manually? So the model is saying that whenever you are given this, the best way to go about this is to first of all express this complex number in the form r cos theta plus I sin theta. If you're able to do this, then if you have a complex number raised to the power n, then this is just the same as raising it to the power n. All right. Now, if you're able to raise it to the power n, so it's going to be Zn, which is what? Rn cosine. So this is the Marbury's term. Cosine n theta plus I sin n theta. That's all. So in fact, that is it. Whenever you are given a complex number and then you want to find Zn, so Zn, for instance, let's say 1 plus I to the power 1000. For this one, it's just going to be Zn. So we are going to get Z1000 to be what? The magnitude. And what is the magnitude? The magnitude of 1 plus I will be the square root of 1 squared plus 1 squared. Okay, I'm coming. The square root of what? 1 squared plus what? Okay, let me write it well. Root of 1 squared plus 1 squared. Cosine 1000. Okay, but then we need to get the argument, which is the tan inverse of 1 over 1, which is what? Tan inverse of 1. (45) or pi over 4. So we can say that Z to the power 1000 is the same as 1 raised to the power 1000. Square root of 2. Square root of 2 raised to the power 1000 cosine, okay, multiplying cosine 1000 times pi over 4 plus what? Okay, let me bring it here. Plus sine of 1000 times pi over 4. All right. So now if you evaluate this, that will be the answer. All right. So this is what we call the Marbury's theorem. All right. So then I want us to look at let's look at some trigonometric identities, and then that will be the end for the complex numbers, and then I will review vector spaces. All right. Because of time, we cannot do matrices, but if you have complex numbers and then you have vector spaces, I think you'll be fine. Okay. So sometimes they can give you some expression. And then they will ask you to use the Marbury's theorem. Let's say you have been given a question like this. Okay, so express sine 3 theta and then cos 3 theta, using the Marbury's theorem. So how are you going to do this? Please, can you hear me? All right. So if you are given something like this, and then you've been asked to express sine 3 theta and then cos 3 theta, the best way to look at this is to apply the, so we can see that there is 3 here and there is also 3. So if I have 3 theta, and then what comes into mind? We know that from the Marbury's theorem, whenever I have cos theta plus I sine theta, and then let's say z raised to the power n, this is good. This is the same as what? Cos theta plus I sine theta raised to the power n. And then this is the same as what? Cos n theta plus I sine n theta. Okay. All right, so that is it. Now let's apply it here. Because we see 3 here, then we can assume that n is 3. So let's try to do z cube and see what will happen. So z cube will be what? Cos 3 theta plus I sine 3 theta. Is that right? But before we can continue, we need to look at it this way. How can we open it up? So now this is what we are coming to do. We are coming to open up cos 3 theta, and then we are also coming to open up sine 3 theta. How can we do that? Let's look at something interesting here. Let's say I have a complex number z1, which is cos theta plus I sine theta, and then I have another complex number okay, let me just write this. Let me just write this. It's actually a formula. Zn plus 1 over Zn. If you have a complex number and add to the inverse, you are going to get 2 cos n theta. And then if you have a complex number and then you subtract from the inverse, you will get 2I sine n theta. Okay. So having known this, what again can we say? So we can say that a special case where n is equal to 1, so for n equals 1, we have z plus 1 over z to be what? 2 cos theta. In other words, cos theta is actually 1 over 2 multiplied by z plus 1 over z. And then z minus 1 over z will be 2I sine theta. So we can also say that sine theta is what? 1 over 2I z minus 1 over z. Okay. Alright, so basically this is what we have. So we can actually apply it right now. In what way? So this is how we are going to do it. Let's try and find cos cube theta. Why are we doing this? Because the question said that we should express sine 3 theta and then cos 3 theta in the powers of what? In the powers of cos theta and then sine theta. So if you do cos cube theta, we will get what? If we do cos cube theta, okay, so let's go back. Cos cube theta is like cos theta cube. But what is cos theta? We know from here that cos theta is what? 1/2 multiplied by everything here. So it's going to be 1/2 z plus 1 over z cubed, which is the same as 1 over 2 cubed z plus 1 over z all cubed. So cos cube theta will be what? 1 over 8 and then what? Z plus 1 over z cubed. Alright. So we need to actually expand this. So if we expand, we are going to get 1 over 8 multiplied by, so for this one we will have to apply Pascal's triangle. So 1 1 2 1 1. The first one is n is 0. The second one is n is 1. This is n is 2. So 1 3 3 1. N is 3. So we are actually here. So we are going to use 1 multiplied by, okay, let me just leave it. Z multiplied by 1 over z. Okay. Here will be 3. Here will be 0. Plus 3 multiplied by what? 1 over z. Here will be 1. Sorry. Here will be 2. Here will be 1. Plus 3. 1 over z. 1. Z 2. Plus okay, so plus 1 over z 0 z cube. So you realize that cos cube theta will be what? 1 over 8 multiplied by z cube plus 3 multiplied by 1 over z, so which is the same as 3 over z, plus, so this one, the z will cancel one of them, so 3z, sorry, plus z cube. All right. Okay. So from here, okay. So cos cube theta will be 1 over 8. into bracket. So all right, oh sorry, there was a mistake. Here is supposed to be Z, and then here will be 1 over Z. I'm really sorry about that. And then for this one, here is supposed to be Z, and then here is supposed to be 1 over Z. Finally, for this one, all right, so 0, 1 over Z cube. Yeah. So it's supposed to be Z cube plus 3Z plus 3 on Z all right. And then plus 1 over Z cube. So now if you simplify everything, you are going to get oh sorry, okay, thank you. So if you simplify, you are going to get Z cube plus 1 over Z cube plus what? 3 into bracket Z plus 1 over Z. But what is Z cube plus 1 over Z cube? So we know that Zn plus 1 over Zn is 2n. Sorry, it's actually 2 cos n theta. meaning that z cube plus 1 over z cube will be what? 2 cos 3 theta. And then z plus 1 over z will be the special case, which is 2 cos theta. So simply put, z plus 1 over z, so 2 cos theta. All right. So if you put everything inside, we are expecting cos cube theta to be what? 1 over 8 multiplied by 2 cos theta by 3 multiplied by what? 2 oh, sorry. You know, this part is this first one. So it was supposed to be 2 cos 3 theta. And then the second one, okay, so this is what I was saying. Zn plus 1 over Zn, which gives us what? 2 cos n theta. And then so Zn plus 1 over Zn gives us 2 cos n theta. And then so meaning that if I have this, so that is why we had what? 2 cos 3 theta, because it was what? Z cube. Alright. And then we are going to multiply 3 by what? 2 cos theta. That's all. So in other words, cos cube theta is the same as 2 over 8 cos 3 theta plus 6 over 8 cos theta. All right. So if I solve for cos 3 theta, then 1 over 4 cos 3 theta will be equal to cos cube theta minus 3 over 4 cos theta. All right. Okay. So please, I want you to do sine 3 theta. All right. So I think we can end on the complex numbers. I hope you have learned something. Okay. So let's move to vector spaces. And then I will close for the day because of time. So please, let's have a 2 minutes break. I'm coming. I'll be back shortly, and then I will introduce vector spaces. Okay, guys. So I'm back. Okay. So let's continue. We are going to look at vectors. Okay. We are going to look at vectors. So the first thing we are going to look at in vectors is so I believe we all have a general overview of vectors. So we will go straight forward, and then all right. So let's spend some 30 minutes on vector spaces. All right. Let's start by solving some of these problems. Okay. So we are going to start with a plus b. So what is a plus b? So 5, 12, and then b is what? Minus 3 minus 6. So if I add, it's very simple, right? It's going to be 5 minus 3, comma 12 minus 6. That's all. So it's going to be 2, 6. Is that right? Okay. So vector addition is really simple. So a plus 3b is going to be what? So a plus 3b is going to be 5 12 plus 3 times b, which is minus 3 minus 6. Is that not it? So a plus 3b will be 5. What is 3 times minus 3? That is minus 9. Sorry. Plus, so 3 times 6, 3 times minus 6 is 18. All right. Okay. So what do we get? So minus 4. 12 minus 18 is what? Minus 6. Okay. So these are just basics of vectors. All right. And then finally, maybe let's take one of them. The magnitude. Okay, let's take the last one actually because of time. So a is what? 2i minus 4j plus 4k, and then b is what? 2j minus k. Let's add the two. So a plus b is going to be 2i, because there's no I here. The j component is going to be minus 4j plus 2j, then plus 4k minus k, because when you add, this is already negative. So then you are going to get 2i minus 4 plus 2 is minus 2. So 2i minus 2j plus 3k. That's all. Okay. And then if we have been asked to find the magnitude, let's say magnitude of a plus b, let's say. So a plus b will be the magnitude, which is what? 2 squared plus minus 2 squared plus what? 3 squared. And what is this going to be? Please, can you hear me? Okay. So 2 squared plus 2 squared plus 3 squared. And what is that? So we will get square root of 17. All right. So that is it. I want us to move forward. All right. So the next thing we are going to consider is the unit vector. Okay. So what then is a unit vector? A unit vector is nothing but vector over its magnitude. That's all. So let's quickly do this. Okay. So let's look at a unit vector. Sorry. So a unit vector is a vector which is moving in the same direction as the vector we are interested in. All right. So if you want to calculate a unit vector, let's say for A equals minus 3i plus 7j. To find the unit vector, you will have to say that the unit vector is 1 over the magnitude of A multiplied by A itself. So in other words, a unit vector is like the vector divided by its magnitude. That's all. Which is what? So the vector here, minus 3i plus 7j, then you divide it by the magnitude. And what's the magnitude? Minus 3 squared plus 7 squared. So then the unit vector is going to be minus 3i plus 7j divided by what? The square root of 3 squared plus 7 squared. And what is that? So let's say square root of 58. So in other words, the unit vector, which will be in the same direction as this vector A, is nothing but 3i over root 58 plus 7 over root 58j, and that is the unit vector. All right. Now let's solve the next example. Example B. So let's call that vector, maybe let's call it vector B. So for vector B, HI minus J plus K. So what's the unit vector? So the unit vector is going to be the vector divided by what? The magnitude. So 1 over the magnitude of B multiplied by vector B. That's all. So it's going to be okay, so 1 over the magnitude. But what is the magnitude? First of all, let's calculate the magnitude first. So the magnitude of vector B is 8 squared minus 1 squared 1 squared. So the square root of this, what is it? So you are going to get the square root of 8 squared plus 1 squared plus 1 squared. Please, can you hear me? Okay. So it's going to be all right. So please, I'm waiting for the answer. So that is square root of 6. Is that right? Okay. So it's going to be 1 over square root of 66 multiplied by 8I minus j plus k. So in other words, that is the unit vector actually. Okay. Okay, so that's the concept behind the unit vectors. All right, that's the concept behind the unit vectors. So sometimes they will not say find the unit vector, but they will tell you that find a vector which is in the same direction or a vector which is parallel to the given vector. So that is also the unit vector. But sometimes they will not tell you that find the unit vector. I hope the concept is clear. Enough of the unit vectors. So now let's move to so this is to say that if I have vectors and then these vectors have the same direction, then the unit vector is the same. All right. In other words, we can use the unit vector to find the direction of a vector by multiplying by finding the unit vector. We will get the direction of a vector, or in other words, the direction vector actually. I want us to look at the dot product, and then we will look at, so we want to, I want us to look at the dot or scalar product, and then we will look at the cross product. Okay. All right. So let's look at the dot product. So what is the dot product? So the dot product is nothing but, as the name suggests, A dot B. So that's how it is read. But ideally, what happens is that whenever you have the dot product, you are actually dealing with multiplying the scalars or the numbers. So for instance, let's say A is given as A1I plus A2J plus A3K, and then I have B as B1 okay. I'm sorry for that. So let's say that B1 is B1I plus B2J B3K. So the dot product Okay. So the dot product is going to be A dot B, which is A1 multiplied by B1 plus A2 multiplied by B2 plus A3 multiplied by B3. That's all. All right. Sorry. So that's the dot product for you. Okay. Physically, what does this mean? So physically, what this means is that if I have two vectors and then I am not interested in the vector product, or let's say I am interested in the scalar quantity, then the scalar quantity is given by just multiplying the scalars. In other words, considering only the numbers without looking at the vectors. All right. So now let's solve some examples. But before we solve an example, let's look at something interesting here. We can also say that the scalar dot is actually A B cos theta. So this is 1 and this is equation 2. These are all correct. So we can say that A dot B is actually A1 dot B1 plus A2 dot B2 plus A3 dot B3, and then at the same time we are also saying that A dot B is actually the magnitude of A, the magnitude of B, cosine theta. All right. So with the help of this, we can actually find the angle. Whenever I want to find the angle between two vectors, I can use the scalar or the dot product to find the angle. Okay. So let's solve some examples. Let's say that you have been asked to find the angle between two vectors. Okay, you've been asked to find the angle between these two vectors. You are going to use the dot products, but in the question they will not tell you use the cross product or dot product. They will just ask you what is the angle between these two vectors. Okay, so given two vectors like this and you've been asked to find the angle, it's simple. So we know that A dot B is equal to magnitude of A multiplied by magnitude of B cosine theta. And then we also know that A dot B is A1 dot B1 plus A2 dot B2 plus A3 dot B3. So equation 1 and equation 2. Equating the two equations, I can say that cos theta cos theta, which is the angle between A and B, is given by A1 B1 plus A2 B2 plus A3 B3. Then I divide everything here by A so A B. All right, so for this one it's going to be cos theta is going to be 2 multiplied by 5. So this is the A1, this is the A2, this is the A3, B1 B2 B3. So 2 multiplied by 5 plus 2 multiplied by minus 3 plus minus 1 multiplied by 2. Then I divide everything here by the magnitude. So the magnitude of A, let's quickly do this. The magnitude of A is square root of 2 squared plus 2 squared plus minus 1 squared. And then the magnitude of B is 5 squared plus minus 3 squared plus 2 squared. So whatever you get, then you put it inside. Okay. So A is going to be, the magnitude of A is going to be square root of what? 2 squared, which is 4, plus 4 plus 1, which is 9. So square root of 9 multiplied by 5 squared, which is 25, plus 9, which is 31, plus 4. So square root of 35. Now if you want to find the angle theta, theta is going to be cosine inverse of whatever you are going to get. So first of all, compute this, and then cos inverse of answer is the angle between the two vectors. So please, what is the answer? So what is the answer, please? Okay, so what is theta? All right, so what is theta? All right. So please, I'm waiting for you guys. All right. So theta is what? 83.52. Okay, thank you. That's correct. All right, so it's correct. So I hope the concept is clear. All right, so that is the dot product for you. You have to be very careful because whenever you are dealing with the dot product, sometimes you can use it to find the angle, but they will not tell you that use the dot product. They will just tell you find the angle. So it is up to you to know that it is the dot product that can help you. All right. Okay. So in fact, there are several things that we can do. But let's look at something interesting here. Whenever I have the dot product, A dot B, it can be written as what? A multiplied by B cos theta. Which means that if theta is 90, then cos 90 will be what? 0. Therefore, for perpendicular vectors, so for perpendicular vectors, the dot product is always equal to 0. Please, you have to bear this in mind. Whenever you have two vectors and then they are perpendicular to each other, then the dot product is 0. So sometimes they can give you a question and they will say that find vector A. Maybe find the component of the other vector, given that this vector is perpendicular to that one. So it is you that you have to know that if it is perpendicular, then the dot product will be 0. I hope the concept is clear. If it is perpendicular, the dot product is 0. All right. And then let's look at projection. So scalar and vector projection. So whenever we talk about projection, we are talking about the fact that we can project a vector onto another vector. Okay. Now let's go straight forward. So we said that A dot B is A multiplied by B cosine the angle. Now this means that I can also write this as so B, make B cos theta the subject, is going to be A dot B divided by A. But what is the significance of this? So let's say that you have two vectors. Okay. And then let's say that one vector is here. Let's call this vector vector A. And then let's call this vector vector B. Okay. So if you want to project, so let's say that this is theta. Theta is the angle, right? So if you want to find the component of B along A, so we call it B along A, then it is given by what? B cos theta. But what is B cos theta? B cos theta is what? A dot B divided by A. Simply put, whenever you want to find the component of a vector along another vector, then it is the dot product divided by the magnitude. All right. So we call this B cos theta the projection of B onto A. So B cos theta is called, so B cos theta is equal to projection of B onto A. Okay. So in other words, we can also rewrite this as So component of B along A. So it's going to be A divided by A dot B. Now think about this carefully. This is interesting to know that this is also the same as saying that 1 over A multiplied by A and then dot B, meaning that the unit vector along A dot B. So in simple terms, if you want to find the component of or the projection of B, so if you want to find the projection of B onto A, then it's going to be what? The unit vector of A dot B. I hope the concept is clear. All right. And then there is what we call the vector projection. So for the vector projection, you multiply by the unit vector. So for vector projection, it's going to be 1 over A multiplied by A dot B, and then you are going to multiply the whole of this. So you are going to multiply the whole of this by the unit vector, which is the vector over the magnitude. So in other words, A dot B divided by A multiplied by A over A. Okay. So you end up with so you are going to get A dot B divided by magnitude of A squared multiplied by A. Okay. All right. So let's solve an example. I'm trying to look for an example. Okay, let's solve this question. let's solve this question. All right. Okay. All right. So let's find the scalar and vector projection of B onto A. So the first thing to do is that for the scalar projection, it is the same as B cos theta, which we know as A dot B over scalar product of the magnitude of A. So let's calculate the magnitude of A. So square root of -2 squared plus 3 squared plus 1 squared. And what is that? So please, someone should help us with the magnitude. All right. So it's going to be square root of 14. All right. Okay. Now, so projection or the component of B along A is the dot product. So we are going to do the dot product. So 1 multiplied by -2 plus 1 multiplied by 3 plus 1 multiplied by 2. Then we divide everything with root of 14. Okay, so if we divide this by root of 14, what will be the answer? And that is the component of B along A. Let's look at the vector projection. So for the vector projection, what is it going to be? So it's going to be the scalar projection multiplied by the unit vector. So we will carry everything which we know here, which is the scalar projection, then we'll multiply by the unit vector. That's all. So it's going to be square root of, okay, we are waiting for the scalar projection. Anyone to give out the answer for the scalar projection? Okay. So 3 on 14 root 14. So basically it's going to be 3 on 14 root 14 and then multiply by the unit vector, which is what? 1 over root 14 multiplied by a, which is minus 2i plus 3j plus k. Alright, so root 14 will cancel root 14, so 3 on 14 so it's going to be 3 on 14 minus 2i plus 3j plus k. Alright, so what do you observe here? You observe that we got for the scalar projection we got a value which is a scalar, but for the vector projection we get a vector. Alright, so that is the difference.